Hi everybody, my name is Michael Stover. I'm with the Heat Transfer Products Group. We manufacture equipment, medium and low temp refrigeration equipment from a half horsepower up to about 100 horse. So we're going to be talking today about those types of applications and how it relates to A2L and the changes coming. So think of an evaporator or unit cooler in the space, a condensing unit outside from temperatures 50 degrees down to minus 30. So it's kind of where we're living in. And this A2L part of it is specifically in that medium temp, low temp range. So I'm going to touch base quickly on one of the changes that came through for we were talking about refrigeration or refrigerants earlier. So in our neck of the woods, the SNAP 26 rule came through and it approved several refrigerants. Where our part of the industry is going and settling on are these. We're going to see R454A, R454C, and R455A. Those are from a manufacturer standpoint, those are the numbers we're settling on, the refrigerants we're settling on. And the other part that affects us is part of the AIM Act, and what that does for us in our industry is it limits the GWP requirements. So if we have a total system charge of 200 pounds and under, we can use a refrigerant that's got a 300 GWP, which is 454A. And if we're over 200 pounds, we have to use a refrigerant that has a GWP limit of 150. So that is 454C and 455. I get up here on the screen, these are probably teeny tiny, but this shows your 454A and that you can use it in total less than 200 pounds, and then it shows you the other two alternative refrigerants. And there have been several phases to this change in our industry. Part of it was some packaged equipment, which is all done. We have our systems, which would be new installations coming in, which we're introducing new product lines. Right now, we're going to see a lot of focus on smaller equipment because that's what UL has approved for us and what we have numbers on. So the examples we'll see through here are some smaller equipment. But the other part of this regulation is the current product line will continue on under they have a repair and replace clause. So what that means is if you have somebody hits a condensing unit with a fork truck or something like that, you can replace the condensing unit or the evaporator and not have to replace the whole system, make it A2L. There's a few conditions on that, which we'll see on this next slide here. So this is down here is what they're calling new installation, right? Where it's all the equipment's coming in new. The capacity is increased from what it was. Or this last one down here is more focused on rack, but it's saying 75% of the evaporators and 100% of the compressors on the rack, like those are replaced. We trigger any of these, and you've got to bring the whole system into A2L compliance. And as we go through the slides here, we'll see what that involves with leak detectors and piping, kind of how we're going to have to rethink what we do or what we've done for a long time. All right, so, I'm not going to stick super long, but what I want to point out with the way a lot of manufacturers are going, right, we're starting this new product line, and basically we're putting a new refrigerant designator in our model numbers. Those will have to be distinct products. So if you have a 454 or an A2L requirement, you'll have to use equipment that is specifically labeled and applied A2L. If you're using a high GWP refrigerant, you'll have to use a product specifically, labeled for that application. So what that means is, that current product line that we're still using, that we use HFCs for, that will continue on. That'll be a specific part number that's different from the A2Ls because there are some differences in the equipment. So the big difference, the condensing units, there's not a lot of impact on them. There are A2L specific compressors. Those are backwards compatible. So from a replacement standpoint, the compressor will be the same. But from our application standpoint, we'll have an A2L specific compressor. We've made some improvements to our equipment along the way, but you'll see, red labels, red caps, and then this signage on the outside. So other than that, if you walk up and you're trying to figure out which is which, there's not going to be a lot of difference. And what this really looks like, in the wild. Here's something at the plant, but you can see the red caps. That signifies the A2L. We've got A2L tags at the access ports, and then we'll see in another slide here. You can see that there's the special labeling that says, "Hey, this is an A2L, contains flammable refrigerant." So all of the new product line condensing units will meet this. You'll see that as a change in what we're doing and what the industry's doing. Just a quick comparison on the refrigerants. 454A, like I said, is, think of smaller applications, restaurants, convenience stores, things like that, under the 200 pounds. It's most similar to 448 that we've gotten used to at this time. If we go into the higher system charge, and we need the lower GWP, we would use 454C or 455A. Higher glides, the temperatures, the refrigerant behave a little differently. The thing really worth noting is that on 455A in our design and application, we see some limited applications on the higher ambient applications. So that's a concern when applying our equipment for 455A. And not to get hung up too much with numbers, but I did want to throw some examples out because it's important. If we go back to 454A, we're saying a very similar capacity, right? And you can see that here in this column. When we go to 454C and 455, we take a penalty. We touched on the glide and how that affects our equipment, right? So that's what we're seeing here in a lot of instances. But you take this 3-horse equipment, it was good for 28,000 BTUs. You may come through here and find out that, I've got something off there. Let's look at this example. I apologize. The 5-horse, 43,000 BTUs. We can see that for the 454A, we can keep the same equipment, but to go up to the other refrigerants, we'd have to go up a horsepower size. So that means when we're reviewing that in a swap out or change out, that means there could be more electrical requirements, NCA and MOPD, so we'll have to make sure that's reviewed. And physically, it could be a next size up chassis, so we have to review that. There's not a like for like anymore where, horsepower is a horsepower is a horsepower between all the refrigerants. We've got to go through and really take what's there if we're replacing equipment, take what's there, go back to the catalog, see what that published value was, and then make a new selection, because this will absolutely impact the equipment and how we apply it. And again, on the low temp side, we actually gain capacity with 454A, but again, we take a hit on the other ones. So you can see, we get a 14,000 BTU here for 4 horse, and you have to go up to a 6 horsepower. So again, we really see that we saw this with 448 compared to 404. The low temp is where we really take a hit on capacity. So again, really just the focus or the takeaway for these slides is, we're going to have to go back. We're going to have to get the capacity of what's there. We're going to have to take a look at what refrigerants required based on the total system charge, and then we're going to have to make a fresh pick from that, and then we'll have to review electrical and physical requirements of it.
Quick question on the total system charge. Are you referring to, let's say it's like a multi-circuit unit? Is that the charge of all the circuits, or is that a charge per refrigeration circuit in a dual compressor system?
So with this, the GWP part, it is basically the circuit. So if you had, 2 separate refrigeration circuits in one chassis, it is per circuit. And so think of how much you'll have to charge that part of the system with. If it's a shared, like a rack or something like that, obviously it's the whole part of it.
Right.
But for our type of equipment, if you've got a shared chassis, with 2 independent refrigeration circuits, that GWP requirement goes to the circuit and not to the whole.
Gotcha. So that can help you go with the 4A model as opposed to going to 4C.
Yeah, yeah.
Split it up like.
Yeah, but when you get, so the counterpart to that is the challenge though, is you're getting into the larger horsepowers,
Right.
which means you're gonna quickly get up to that 200 pound charge limit,
Right.
which is gonna force you over to a 454C. Now, something that we'll see, you know, that helps us solve some problems is, you know, if you're starting from scratch or you're doing a whole rebuild, you could divide it between 2 smaller systems and maybe that gets your total system charge down low enough.
Right.
You know, definitely there's going to be a lot of ways to look at things differently that we could try to solve, you know, solve a problem with.
Gotcha.
Mike, for that charge limit, like if it's a split system, that includes the evaporator, the line set, everything?
Total system charge, that's right. All right, so just key takeaways from the condensing unit side of it. You know, the nomenclature part of it, we will, again, our current product line, or, you know, most manufacturers, right, we're continuing it on the repair and replace so that we'll be able to have a like-for-like replacement if we need it. You know, there's several components that we've replaced to come up to AWEF compliance. We're focusing on 454A, 454C, and 455A. You know, the A2L compressors are backwards compatible, but when they mount into the equipment, it is refrigerant specific or A2L or non-A2L specific equipment. Again, just to touch on it, but you know, we're adding a model number or a letter to our nomenclature to designate the A2Ls. So this is where we see the biggest change. What we are seeing, the coils that are mounted indoors in the space, we have, you know, you can see leak detectors here on some of the bigger coils. We'll actually have leak detectors on both ends. We're going to have a leak detector terminal board, a transformer, some relays, and all of that from us will come pre-wired and installed into the control circuit. They'll have to be, we'll see that we got to tie some things together, but you know, this is definitely a big change. And you know, the other part of that we'll see a few examples, but what we've got to do with the calculation is to see the maximum potential refrigerant that we can leak into the space, and then there's calculations done based on that, and where we evaluate whether we can or can't use it, and then the type of mitigation that we would need for that. So with that, the way we see these coils being applied is you're going to have to, where we traditionally would put a solenoid at the evaporator, we're going to have to move that outside of the box, and then we'll have a suction check valve just outside of the box. And so the thought is that if we have a leak in the space, you know, we'll trap whatever refrigerant is in the space, and we won't leak the whole charge into the space. So that's a new thing that we've not done, you know, with the solenoid. We've traditionally, you know, done one solenoid to feed the whole trunk line, but that'll be new how we need to do it. And here's just, you know, some real world pictures. The coil in the picture is upside down because it's at manufacturing, so this will actually be your bottom drain pan, but this is your leak sensor, you know, fusing, and you know, so this will be required on any of the A2L approved evaporators.
What's the basis on the design of the leak sensor?
What do you think? It's
How does it
like
work?
a sniffer.
Yeah, how does it work? I mean, no, it's sitting there all the time running. I'm just, you know, Visla makes it. I mean, I'm just wondering how it actually works. I have a
Like when it
blank, I don't
detects a
know.
leak, what it does?
Excuse me?
When it detects a leak, what the system does?
No, what does it do? How does it detect the refrigerant?
It is like a sensor like you would have on a rack or any other thing that it picks up parts of the concentrations of the refrigerant, the parts of the refrigerant.
It's a chemical reaction or an infrared absorption?
I don't know that answer.
That was basically what I was asking.
Yeah, I could certainly connect with you after, and I can get your
Yeah.
information. I'll follow up with that. I don't know that part of it. So again, just a quick example of you know, coils. Here's where we talked about again with the glide, we gain efficiency in the coil. So what that means, or where that could potentially get us in trouble, is if we're looking at air changes in a space. if we've got really big coils and we have two fan coils in the space, and now we can get away with one fan, so we'll have to take consideration of that. We look at some of these, this example of a 19,500 for 404. We can go down to a 3 fan. So we again with the we have a lot of folks in the refrigeration industry that they can go in, lick their finger, hold up, and say, all right, I should have 3 fans here, 3 fans here, and 5 horsepower. And all that's changing with the refrigerant because it's not your capacity of your condensing units, now different, and your evaporators are different. We saw a lot of pushback initially when we introduced 448, because we saw the same thing, right? Less fans. People are used to walking in a box and thinking, well, it needs 3 fans, and now we're selling 2, and it becomes questions from that. But air changes would be the big impact on the design side of that. All right, so our leak detector, what happens when we sense a leak? And we'll see how it's wired and tied in a few slides, but basically the way the system works is defrost going to terminate if it's in defrost, the solenoid's going to close, the system's going to pump down. So when pump down is done, we've got as much refrigerant out of the low side. If we've got our suction check and our liquid line outside of the box, we pulled as much refrigerant out of that part of the system and moved it outside as we can, so that we minimize how much refrigerant we can leak into the space. So we're gonna pump down. The fans are gonna come on and stir the air, and then an alarm relay will close on the sensor itself. So if you want to tie something outside of that to be aware, a light or something like that, that there's been an alarm. We do have an electronic controller basically, and it does the same function, but it basically will log a leak in that. After an hour, there's an hour holdout on the sensor. After an hour, if the concentrations have come down low enough, the system will come back on and run. And it'll run since the concentration gets high enough again, and it'll go through the same thing until you run out of refrigerant, or somebody sees that there's been a trip and goes and takes care of it. All right, so this is how, this is a just visual of what I was talking about. So this is your space, your cooler, freezer, and what we're doing is, liquid line solenoid just outside the box and a suction check. So we pump down, we get as much refrigerant out of here as we can, and now the only refrigerant or the maximum we can leak is what's contained here. What we are working through, there's 2 ways to take this isolation philosophy. You can do it per coil, or you can do it as a group, right? We'll see as a group in just a second. But so what this will require is a solenoid on each coil. If you have multiple coils, they'll be tied together here so that the coils work together. So if one sensor on one coil detects a leak, both coils work together to pump down, to stir the air until it comes back on. So what this helps us do is this minimizes the amount that we can leak into the space. This next example of the group isolation. So we've got these right outside of the box, but now you have all this extra piping that's in the space that we could leak. So it could certainly be evaluated as a group isolation, but what you're going to find out is, if you run into a situation where you've got too much charge for it, you could split them up into individual coils, or you could, do more systems, smaller capacity. If you run into an instance where you aren't going to meet the requirements. Again, at the end, we'll talk about the calculation and what that really means. So those are the 2 means of isolation. This, for the sake of, most users, will be the easiest way, because this calculation is going to be pretty simple, and we're working on a tool for that, of how much refrigerant is in between these. When you get to this group isolation, you got to look at trunk lines, and then what's coming off the trunk line, what diameter is that, and how many coils is it feeding. Calculating this for the average user would get, complicated pretty quick. And so where this changes our philosophy on piping, typically you would see, the liquid line of suction run in the space, and, just run down to the coils wherever they are, and back out of the space. But what we'll have to do is, because the liquid line especially, right, you carry a lot of weight of refrigerant in it. The thought is, or what we believe is, that main piping is going to move outside of the box, and then you're going to penetrate in to get the coil and then back out to help keep that that potential leak to a minimum in the space. All right. Any questions on this? It's a lot. It's a completely different change in how we're used to doing it in our industry. For those of you that are doing refrigeration, yeah, it's a big change. So considerations in design and what this means for what we're going to use. Converting the components, changing what we're doing from an existing system that may be an HFC to an A2L, the components are going to be different. We're not going to be able to, go by the horsepower thing again, right? We're back to, even the equipment that we're building today. It's cataloged for 404, 407A, 407C, 448, and 449. So even the stuff we use today, if somebody, is looking to replace that, you still have to come back to what refrigerant is in it. A 3 horsepower with 404 low temp is not a 3 horsepower low temp 448. It's not the same capacity. We saw that with the condensing unit capacity slide. Piping systems incorrectly, making sure that our line sizing is right. I haven't seen any line sizing information on the A2Ls yet, so I don't know if we're going to have to start from scratch on piping or not, or if it'll be close enough. So that will have to be something that's evaluated if we're changing out a system and leaving or trying to leave the pipe run that's there already. Different physical and electrical requirements. So again, replacing equipment that's there, we'd have to consider that. Mitigation levels, which we'll talk about here in a minute. There are 3 different levels of mitigation that are required. Again, the new installation where we would get all new versus a repair and replace situation where we're only replacing part of the system. And, kind of limiting that piping inside of the box is a change from what we've traditionally done. So mitigation, so there's 3 levels of mitigation. For us, we're treating M1 and M2, and we'll talk about this calculation, a little in another slide or two. But M1 and M2, basically we respond the same, which is what I described, right? We pump the system down, we turn the fans on, the system blocks out for an hour, we stir the fans. If the concentration has come down, then we'll bring it back on and run the system. M3 requires the additional outdoor air to be pushed into the box to help get that concentration out. So the challenge with that obviously would be, your box is -10, it's a nice warm, humid Atlanta day, we get a leak detection, and we push all that warm, moist air into the room, that's gonna be a problem any way you put it. So that's where, when we start looking at that single coil isolation to help that mitigation level stay where it needs to be, that's a consideration. And also more condensing units, less capacity will help us manage that too. So, from our perspective, we're going to stay away from M3 applications as much as we can. If we do end up with one of these applications, an evaluation will have to be done by a licensed professional to see how much air and that type of thing needs to come into the box to meet the requirements. There is actually an upper limit on this, so if there is too much, it'll actually disqualify the application and you wouldn't be able to use it anyway, and we'll see that when we talk about the calculations. So again, if we get to that point where we're in this M3 or the system is just has too much refrigerant for the space, then we can take a step back and put smaller condensing units, more quantity so that we have that potential less in the space. All right, so there's two factors on the calculation we're doing. The first one is the maximum releasable charge. So we're working on, a program that will do that calculation for you. You'll have inputs that you do, but this will do. But basically, the inputs of that are going to be your refrigerant, what the model of the coil is, your line run, both the liquid and the suction, the length and the diameter, and then the box interior. So from that, you're going to calculate a maximum releasable charge into the space. And out of that calculation comes the answer, right? You can put, 100 pounds of refrigerant into the space. And then it compares that to the mitigation levels to see, M1 is this much, M2, M3, so that, you know which level of mitigation to apply. And the other part B to that calculation is there's a minimum area requirement also. So what that does, your inputs again are your maximum releasable charge, your internal box dimensions, and your refrigerant. And basically it gives you a solve, say you gotta have a box of 100 square feet for this to be applied. So if the box is under that, again, we have to take a step back and see if we're doing group isolation, we could do individual isolation, or if it's, maybe instead of one condensing unit, we've got to split it into two smaller condensing units and apply it that way. And basically the output of that part of the calculation is a pass-fail. So either you're under that requirement and it's okay, or you're over it, you got to solve it. And either of those two that are, if either of those two fail, like if we're too high on the M3 or we're too small on the square footage, we gotta go back. You gotta go back and look at it. Any questions on that?
My question. On the M2 and M1 and M2, how do you change the concentration of?
You disperse it in the box. So it's really, if the concentration, because the sensors are in the coil, right? They're in that drain pan area. So if there's a leak, it's going to be most concentrated in those return ends of the coil. So really what it's doing is distributing it out into the box. So the concentration really, you're diluting it into the box. It is all you're doing.
So you basically spray in inside.
Yeah. So you bring that concentration down low enough that because there are, there's a minimum point to which it really becomes a hazard, a flammable part of it, right? So as long as it's below that, even if there's a flame or things like that, there's no concern. So that's why we're trying to stay below that part of it. And so if we're leaking, around the coil, we just want to dilute that as much as we can. And then, again, with these other calculations, they're also looking at, is there enough charge within this piping that if we leaked it into the space, is that a concern? So we're kind of evaluating it that way. So when we turn the fans on, if we do leak the whole charge that's between the solenoid and the suction valve, if we leak that whole charge and we spread it all throughout the box, is it still low enough that we're not worried about a situation where we have a fire or something?
I'm just thinking about like new projects, new builds, new designs. So with the considerations we were talking about, I imagine if it's like a new project or you're early enough in design, there's probably a valid conversation with like an architect or whoever, where because the box dimensions themselves obviously play a big factor in this calculation.
Right.
So there could be worthwhile to say, hey, because of the way the numbers shake out, if we can modify the box size by some, add a little bit of square footage or whatever it may be, to a point that doesn't dramatically affect the load.
Right.
But there could be some kind of give and take there to mitigate some of this issue.
Yeah. And one of the things, I don't know if y'all know or not, but this part of the regulation, it's not on manufacturer date, it's not on ship date, it is on commissioning date. So if you buy equipment this year and it's not started until January 2nd and you install it as, a high GWP, you are in violation of the standard or of the regulation. So that's a huge change in the industry. It's always been on, as long as we get it out the door by the end of the year, anybody can apply it. That's not the case here. It is all about when it started up. So stuff that we're looking at toward the end of the year that would maybe slip further out or we would be concerned, we want to absolutely look at it, for an A2L option. Again, we've got the small equipment available, where the larger equipment should be available in June or July, so we can start that conversation then. But yeah, you could absolutely kind of change the volume of the box and see how that impacts the number. If it changes your runtime, if your runtime's low, and you increase it, so you have an extra hour of runtime, and that's still the selection's still okay, then absolutely you can add 10% or 5% to the box and just reevaluate the equipment.
And I hadn't thought about the last bit, so I guess like if there was a project in design now, but it's not gonna break ground until end of the year, equipment may not, be installed or started up until sometime next year, you're pulling home to the new standard, the next year's standard.
Yeah. Again, commissioning date, not starting. Or excuse me, commissioning date, not manufacturing. Usually I stretch this out to 45 or 50 minutes, but everybody's pretty quiet today, so either it's a really boring topic that nobody cares about, which sometimes I don't, or it's, yeah. So, any questions about the refrigeration side of it? Looked at meeting time.
Did you ever encounter a situation where we have an M1 and M2 medication, but every time the leak was so frequent, then you exceed the threshold of M1 and M2, and then you have to, open the door and paint them.
Well, again, that's where, the size of the box, right? We do that area calculation and the maximum releasable charge. So between those two, the thought is that, we know the amount of pounds in the system because we're going to do that calculation. And we know that through the evaluation that, even if we leak all of that into the space, there's still not enough for it to be concerned. So that's where the M3, if we hit that M3 level and we're worried about that concentration again, that's where we would bring the outdoor air in to kind of flush that out and move that along. But again, for a cooler or a freezer, that's going to be messy because everything's going to turn to condensation. It's going to rain in the box, and it's just So again, our goal or my goal as a manufacturer, somebody that's going to need help then is just completely steer away from an instance where we have that M3 level.
It's a wonder they're not requiring continuous ventilation.
Sir?
It's a wonder. I was looking at the whole thing and remembering talking to people before and seeing coils, how many times I've had to fix coils and the way the airflow can shield the detection of the leak and where it is on the coil, drive crazy. But and I was saying that it's a wonder with that, your whole space could be filled up before the detector finally sensed it and went off. And you could be in terrible conditions. And yet there's only airflow, you're saying, signals in by the controls when the condition is met and it triggers from the sensor. So you could hit right up there close to it in bad conditions. It's a wonder they didn't see it like that and cause you to say, well, you got to put a counterflow heat exchanger on this box, and approaching the limit of counterflow heat exchanger. That's a long time. But so you'd continuously vent the box. This is,
But again, that's the maximum releasable charge calculation into the box, right? So they're limiting how much can go into the box, which means we don't get to that point.
Yeah,
where we see that, where we would get to that M3 level, think of things like blast coolers or blast freezers where we just have a pile of equipment in a space relatively small in comparison. So, convenience stores, restaurants, typical cold storage applications where you're bringing product in and it's stored, you're bringing it in close to temperature and stuff. We don't expect to get anywhere near that M3 level. It's where, you've got a box that, is this size and you got coils wall to wall to just get, you're rolling in product that's 150 degrees and you're trying to get it down to minus 20 in 6 hours, that lopsided type application where you just got a bunch of equipment in one space. Most typical applications, we don't expect to get to that M3 level. And even if you do, you can go back and evaluate it, add another condensing unit make everything a little smaller, redo your calculations, and see if that gets you down to an M2 level. Is that how we would address that, is steer clear of M3? Yes, sir?
So the designation of M1, M2, M3, that's application based on like the size of the space, whether or not the equipment goes into one of those levels?
Yeah, that's right. So, you know, the two parts of that, right? This is the maximum releasable. You've got your refrigerant, what model coil it is, because that's an internal volume part specific to our equipment. So we know that part, and our calculator will have that. So it'll be the coil model, from your point of isolation, the length and size of the liquid line, and to the point of isolation, the length and size of your suction. So yeah, it's going to be specific to that equipment in that specific box. And so that,
Michael, sorry, that M1, M2, and 3 threshold, are those like ASHRAE standard 15? Like, is that like a parts per million number?
I think that is we referenced to the 2-89603. It's a UL standard, a UL requirement, yeah.
But there's like a restrictive number, like parts per million or something that you have that defines those breakpoints, I'm assuming?
No, they have a value published, and through the calculation, you back into their value based on what the refrigerant is, and then these other parameters. So between, this would be for the maximum releasable charge, and then for your minimum square foot, that's where we would look at, these additional requirements. So those two things have to be satisfied for it to be an okay application. If either one of those is not satisfied, we got to go back and look at the design. Yes, sir.
Is there anything you guys need to do for like mitigation on like your high emission sources, like your electrical panel? Like I've seen cases where some guys would do like a nitrogen purge or like an E4 panel just to protect the electrical if there is some sort of leak, just to kind of keep that away from like the fuse or contactors that might spark and some sort of sparking.
Yeah, UL doesn't require us to have that. And again, I think, these calculations, they lead to keep the level low enough where if there was something like that to happen, because I mean, think about it, you could have somebody walk into space and static electricity, like there's a lot of other things than just our equipment that you can have a fault like that.
Right.
So these levels aim at keeping that low enough where if that does happen, because I mean, we've got the electric heaters in, that type of stuff fails, and sometimes, you have the limits and the safeties and things like that, but I've seen people jump those out and catch heaters on fire and that kind of stuff. So, like, the idea is behind it is to do these evaluations such that if it did leak into the space, we still won't reach a concentration to where if there was an ignition source that it would burn.
Okay.
Yes, sir?
So, I see that you've been talking about the refrigerant split systems, right?
Mm-hmm.
So, in the case that you have like a hydro split, right, and somehow in the heat exchanger, the R90 refrigerant travels to the glycol or something like that, is there any answer to that, something like that?
So that type of application is kind of outside of what we do. So I don't have an answer for that. The furthest we go is a glycol water cooled condensing unit, right? But as far as, we don't do anything with R290, the charge limits are terribly small for that. And, our equipment, we don't really, on the low side, we don't get into that refrigerant because of the charge limits.
What was the point? Was it related to like if refrigerant gets into the glycol or the water?
Exactly.
I asked that question. They said, no, it doesn't matter. Don't worry about it.
I mean, I guess, I don't know, I'm completely speculating here, but if
If you get some concentration of refrigerant in the fluid, but the fluid is going to a cold and cool air, then maybe there's an argument that there's another degree of separation there as far as the refrigerant getting into the airstream and then getting into contact with people or anything like that.
But again, those concentrations are very low, or not, but the charge limits are very low. And if you're running that into like an air handler or something like that, I would think.
I guess if you have a split chiller though, like a split system refrigeration inside of a chiller, then you could have a higher charge. So, I don't know. We'll look into that, but it's an interesting question.
Yeah, I'm just curious if there was something to identify as hazards.
Don't ask UL that, they'll make you start doing it.
Anything else? All right, I appreciate the time. I appreciate that everybody had a full belly and the room was warm and almost all of you had not. So appreciate y'all. Thank you for your time.